So, last class I have covered bearing capacity of footings on layered soils and different cases, case 1, case 2, case 3 I have discussed. Then solve a problem based on your data and from plate load test how to calculate bearing capacity of a footing. Then we will start new one, that is your settlement analysis before your design of the foundations. The requirement is your bearing capacity, second part is your settlement analysis. Before I go for your settlement analysis, so what happened before application of building load? Building load. So, look at these two graphs. This is your Qn, one part is your net load intensity versus time, second part is your net settlement versus time, this part is your rho h, generally it is called heave, and second part is your, this is your rho I, immediate, and this part is your consolidation. So, there is a usually in a building what will happen, usually there is a excavation prior to your foundation level, there is an excavation down to foundation level, and because of the excavations, so the magnitude of heave, is small. Look at here, there is a ground surface here, and suppose you want to construct a strip footing or maybe isolated footing, then what will happen? Below the ground surface you do the excavations, take out the soil. Once you take out the soil, then what will happen? Once you make the excavation, so this is your excavation is there, means no soil. So, because of that there will be some heave at the bottom. This heave is small, if you leave this heave for a long time, if there is a deep cut, it may be a larger magnitude, the heave may be larger magnitude. So, once after this excavations, then you laid the foundations, that means foundation load has been applied or constructions gradually. You do these excavations, construct, then construct, lay the your reinforcement cagings. So, particularly you put your reinforcement caging base of your, then do the concreting. So, then what happened, this construction has been done gradually. So, what will happen, then foundation load has come into picture at this level, here at this level foundation load will come into picture. So, what will happen, once there is a heave pressure, if you look at here, there is a heave pressure net intensity. So, once you apply the foundation pressure, this will become 0 and it will counter, somewhere else it will counter, so that net settlement or become 0 or net foundation pressure, net foundation pressure is 0. Then afterwards further increase in load by means of, how the further increase in load, once this construction is over, this is your foundations. After foundation there is a column, it will be connected with your column, column has to be constructed, then beam, then slab. So, slowly foundation loading on the foundation is coming in gradually. So, further increase in load, net foundation pressure increases, net foundation pressure increases. So, what will happen, then the settlement, if I put it, my total settlement, final settlement is, because of your, one is your heave, other is your immediate settlement, other is your consolidation settlement. Generally heave settlement is very negligible, hence it become immediate plus your consolidation settlement. Before I start it, I thought to explain this is, because what will happen, net foundation pressure it decreases because of your heave, net foundation pressure decreases. By application of a load on the foundations, it again start increasing and it becomes 0, that means net foundation pressure is 0, that means heave has to be settled down, this heave has to be settled down against your foundation pressure. Then once you increase and it increase up to a certain level, then it remains constant, or maybe it is a kind of, it may be go in this way or it may be in this way. So, this part is called elastic, this part is called plastic. So, basically behavior is elastoplastic after your heave has been settled down. Similarly, if you compare with your net foundation pressure with time, then net settlement with your time, this is your heave, then it comes to 0, then there is immediate settlement, then there is a consolidation settlement. If there is a deep cut and you leave it for a longer period of time, definitely there will be a heave settlement in the opposite directions. In the opposite directions, it will be heave. It will reduce your net foundation pressure. So, total settlement will be your settlement because of your heave plus immediate settlement plus your consolidation settlement. Because magnitude of heave is very small, that is why it has been neglected. So, total settlement is equal to immediate settlement plus your consolidation settlement. Then start with your part of your, if I write it, rho f final settlement is equal to immediate settlement, rho c is your consolidation settlement. Now, start with your immediate settlement. Then in immediate settlement there are two cases, one is your clay soils, other is your sand or cohesionless soils. A is your clay. In that case immediate settlement is equal to QNB by E 1 minus mu square into IP. Qn is your net foundation pressure, B is equal to your width, E is your Young's modulus of a soil, mu is your Poisson's ratio, IP is your influence factor. IP is your influence factor at center as well as at edge. From where you will get the influence factor? Either this influence factor will be given or you can go for a plate load test. I have explained earlier also. You can find it out what is your influence factor at the center as well as at the edge of the foundation. Why this influence factor has been used in case of your immediate settlement? From there you can find it out differential settlement of a foundations of a footing, so that it can be said the differential settlement is within permissible limit or not. Now, if you look at different values of your influence factor has been given, particularly for a rectangular foundation L by B values has been given. So, M is equal to L by B and IP influence factor, then here it is at the center, here it is at the corner or edge. So, I am just writing, you can get it from book, all books they are provided. So, just I am writing it 10.0. So, it will be 1.12, then 1.5 it will be 1.36, 2.0 it will be 1.52, then 10 it is 2.53, and this value at the center, at the corner, half the value at center has been taken. Suppose this is 1.12, then at the corner 1.12 by 2 has to be taken into considerations. So, E is your modulus of elasticity. For clay generally E is varying from 500 to 700 Cu. Cu is your undrained cohesion, undrained cohesions. The E value has been given. Earlier I could not give this entire table how to calculate E. Other E also you can get it. This is one E is 500 to 700 Cu, 500 to 700 Cu. Other value of E, particularly in case of sand also you can find it out by means of E is equal to C1 plus C2n, we will discuss. Then there are two correction factors. One is your depth correction factor, So, depth correction factor is your settlement of foundation at depth D, then settlement of corresponding surface foundation, settlement of corresponding surface foundation. That means as if foundation is lying on the surface. So, this is your corrections. Another correction is your pore water pressure corrections. I will discuss later in this particularly settlement analysis latter part. Pore water pressure corrections. It will be applicable only in case of consolidation settlement, not in case of immediate settlement. So, that is why I am removing it. Right now we are discussing about your immediate settlement for clay. So, rho I immediate settlement is Qn into B by E 1 minus mu square into Ip. Qn is your net foundation pressure, B is your width of your footing, E is your modulus of elasticity, mu is equal to Poisson's ratio, Ip is your influence factor at the center or at the corner. Once you know Ip at the center and at the corner, then you can find it out if there is a footing here. What is your immediate settlement at the corner? What is your immediate settlement at the center? Based on that immediate settlement at the corner and at the center, you can very easily find it out differential settlement. And correction factor, depth correction factor has to be determined. That means settlement of a foundation at depth D and settlement corresponding to surface foundation, as if taking into there is no depth of the foundation, foundation has been placed at the surface. So, depth correction factor you calculate. Then part B, sand, immediate settlement in case of sand. It has been given by Buisman 1948 for sand, immediate settlement for sand, it is summation of 2.3 P0 by E log 10 P0 plus delta P by P0 into dz. So, P0 is your initial effective overburden pressure, before loading. In different books it is P0, it is sigma 0. So, initial overburden, effective overburden pressure, it may be P0 or P0 prime. I am talking about effective overburden pressure. Maybe you can write it P0 prime, P0 prime, P0 prime. So, it is initial effective overburden pressure before loading. Then delta P, increase in vertical stress, at the center of layer due to foundation loading. E is equal to modulus of elasticity. Now, so there is a case here, layer by layer, if I put it here, I can put it only 4 layers, 3 layers. So, here it is pressure intensity, because of your foundation I write it like this. So, layer 1, 2 and 3 here is your Z1, here is your Z2, here is your Z3 and this is your E1, E2 and E3. Then this will be your P0 plus delta P. You have to consider layer by layer, and each layer you find it out what is the P0 and delta P and P0 plus delta P. P0 is your initial effective overburden pressure before loading. Delta P is your increase in vertical stress at the center of the layer due to foundation loading. This part, stress in soil mass, Bosenick's theory and as well as at the center of your circular loaded, rectangular loaded, point load. This will be discussed after this settlement analysis. Then from there you can find it out delta P increase in your vertical stress and modulus of elasticity E for sand. E for sand has been given E is equal to C1 plus C2 N, which is your kg per cm square. So, for different soil type it has been given the values. Soil type, this is your C1 kg per cm square, C2 kg per cm square. Soil type, first one is your fine sand above water table. Second one is your fine sand below water table. So, this will be 52 and this will be 3.3 and this is 71 and this will be 4.9. Sand medium size sand, then coarse sand, then sand plus gravel, then silty sand, then is your silt. Why I am writing, many books may not be providing this value E is equal to C1 plus C2, you can get it N, SPTN value from the field or maybe geotechnical investigations. Once you take out the value of N and based on your what is the type of soil, from where you can take the value of the C1, C2, that is why I have written here. For medium sand it is 39, here it is 4.5, coarse sand it is 38, here it is 10.5 and sand plus gravel it is 43, here it is 11.8, then silty sand it is 24 and it is your 5.3, silt 12 and 5.8. So, this is one case, these are in empirical in nature, immediate settlement they have proposed. So, it is your Boisman 1948, he has given immediate settlement for sand, it is a summation of layer by layer 2.3 P0 prime E log 10 P0 prime plus delta P by P0 prime into dz, P0 prime or P0, sometimes P0 prime or P0, it is your initial effective overburden pressure before loading. Delta P is your increase in vertical stress at the center of layer due to foundation loading, is your modulus of elasticity and he has given E is equal to C1 plus C2N. For different soil types C1 and C2 has been given, you can pick it what is the soil type. Based on your SPTN value and C1, C2, you can calculate for sand what is the value of your E. Then there are other correlations also given by Bowles 1988. You can look at that book Foundation Design and Analysis by Bowles. So, E is kg per centimeter square, sand, normally consolidated sand, saturated, sand, over consolidated, then silty sand. For sand it is 5 into n plus 15. For saturated sand it is 2.5 into n plus 15. Sand, that means over consolidated sand, it is 7.5 into n plus 24. Then sand with gravel or silty sand, it is 3 into n plus 6. Then sand plus gravel, it is 12 n plus 6 for n greater than 15. Then this is your 6 n plus 6 n less than equal to 15. This is what given by your Bowles 1988. Another relationship has been given by Schumann and Hartmann. In 1978. So, they have given immediate settlement for sand C1 C2 into Q prime minus Q summation of 0 to Z of entire depth Iz by Es into delta Z. So, what they have done, let us consider this is a footing, isolated footing, and this is your variation of your Iz, this is your depth of the foundation, this is your gamma df, and this is your footing load intensity. Then if you look at here, this is your Z, and this value is your Es, and for different depth, suppose this is your Z1, this is your Z2, this is your Z3 up to this depth, then the value is comes out to be here, then here, then here, then. So, this value is your variation of modulus of elasticity Es over depth Z. What is Iz? Iz is your strain influence factor and C1 is your correction factor for depth of the foundation. C1 is correction factor for depth of your foundations, and this comes out to be 1 minus 0.5 into Q by Q bar minus Q, and C2 is your correction factor for creep. It is your correction factor for creep, and this is 1 plus 0.2 log T in years by 0.1. So, Q prime or Q, this is your stress at the level of foundation, stress at the level of foundation, and Q is equal to gamma dF. We will solve problems once your foundation analysis is over. So, basically there are two methods, two empiricals has been used based on your empirical correlations. One is your by means of Buissmann 1948 and other is your by means of Skammertmann and Hartmann 1978. These are the two methods widely used proposed relationship to find it out your immediate settlement in sand. For immediate settlement in clay, it is very clear Q and B E into 1 minus mu square into I P. I will stop it here. Next class I will start this consolidation settlement. Thank you.